So I'll talk about both of those today. So let's first talk about the risks faced by industry, by the public due to lightning and thunderstorms. If we start off with the aviation sector, we know that commercial aircraft get struck by lightning every 1,000 flight hours, which is equivalent to about one strike per year per aircraft, civilian aircraft. They're obviously built to get these strikes. They're built out of metal, so we have a Faraday cage, and therefore there's normally not any damage to these aircraft. But nevertheless, this is a risk and a hazard, and there have been accidents in the past by lightning strikes to aircraft. In this image, you can actually see that this aircraft is actually triggering the lightning, and the lightning is going both up and down from the aircraft to the thunderstorm. The power industry, obviously we have huge transmission lines going across continents, and because they're fairly high up above the ground, these are also susceptible to lightning strikes and damage. And in the US alone, lightning is estimated to cause more than $1 billion in damage and losses to the utilities and their customers every year. So this is a big hazard for the power companies in all countries, especially countries where there's lots of lightning. Now today with renewable energies, wind farms are becoming very susceptible. Obviously, we put the wind turbines in places which have got clear, fairly low topography, and so they're the highest objects, whether it's over the sea or on the land, offshore wind farms. And since the turbines are pointed objects sticking up into the sky, they can also be struck by lightning, and these are very valuable, these turbines. So one strike can cause millions of dollars of damage. And annually, we estimate that 4 to 8% of the modern European wind turbines get damaged by lightning, which is maybe induced by the wind turbines themselves. Maybe they wouldn't have been struck in that location without the wind turbines. Fires are also ignited, especially in high latitudes, by lightning. And so places like Canada, especially if you remember this last summer, and all the fires and air pollution in Canada, many of those fires were ignited by lightning. And we're seeing more and more lightning going actually further and further north into high latitudes in the summers, which could be causing more and more wildfires. And while the number of fires is maybe not the majority is produced by lightning, they're normally very remote locations where it's also difficult to get with fire crews, and they may not be impacting settlements, and therefore they're left to burn, and therefore they can cause up to 80%, if not more, of the area burned is due to these lightning ignited fires. So they cause huge amounts of damage, which is also, you can translate this into emissions of smoke and greenhouse gases, which can further feed back on the climate. So lightning is definitely a factor here when we're talking about wildfires. Obviously, the public is struck by lightning. Just last week, there was a video of some soccer players in Indonesia going around the internet where someone was struck by lightning and died, but it happens quite often. And we estimate, although we don't have good numbers, about 25,000 people are killed every year by lightning, and maybe 10 times more than that are injured. In fact, most people are not killed by lightning, but it does cause burns or damage, especially neurological damage, because this is electricity going into your body. And as population grows, we're also having more people in harm's way. There's evidence that in Africa and in India, the number of people, the casualties from lightning are increasing. This may be due to climate change, but it may be due to simply more people living in those countries. And finally, some statistics from the insurance agencies. Here you can see a plot showing that the lightning-related insurance losses in the United States are linked also to increasing temperature, or basically summer temperatures. When the temperatures increase in the summer, we have hot, humid days, we have more lightning and more damage from lightning, thunderstorms, and therefore this is also something to maybe to worry about in the future. So let's talk a little bit about lightning. So lightning is generated in thunderstorms, which get charged through microphysical processes in the cloud, similar to the production of rainfall through collisions and coalescence between both droplets and ice crystals. We have charge transfer on the microscale and then separation on the macro scale. And when we look at, in general, at thunderstorms, we see that in the top, in the colder part of the cloud, which especially in the anvils, which are maybe below minus 40 degrees and basically only ice crystals, we have positively charged particles in the upper part of the clouds. In the lower part around, and it's based more on temperature than altitude, so around about the minus 10, minus 15 degrees, we have negatively charged droplets and ice crystals and hail, which will give us this negative charge center, sometimes a smaller positive charge center at the bottom. But the main dipole is this positive at the top and negative at the bottom. And when the electric field between these sensors, as well as the field which can be induced at the ground, when these fields pass a certain threshold, then we get what we see as lightning, which is actually to short circuit this field and to reduce the fields. So most of the lightning in clouds is actually between these charge centers, what we call intra-cloud lightning. We can also sometimes get between clouds. And what we often see ourselves from the ground is what we call cloud-to-ground lightning, which is generally bringing the lightning from the negative charge region towards the cloud. And therefore, we call this negative cloud-to-ground or negative CG lightning. It's possible that we can also get from this pocket of positive, and also from the top of the cloud sometimes we get positive lightning coming to the ground, bringing positive charge. And therefore, we can divide the cloud-to-ground lightning to positive and negative polarity. 90% of the lightning coming to the ground is negative polarity. A small fraction is the positive polarity. But out of the total, we have maybe 75% of all the lightning is within the cloud, and about 25% comes to the ground. We can also have other rare types of cloud-to-the-air lightning, and other types, but it's mainly the intra-cloud, between the pockets in the cloud, and the cloud-to-ground lightning. Now, in addition to the direct hazards to infrastructure and to people and to windmills, lightning can also be linked to different types of severe weather that we see, whether they're flash floods or tornadoes or hurricanes, hailstorms, windstorms. When we study the fingerprint of lightning activity, we can see that there are changes that occur in the lightning activity during thunderstorms and during severe weather. And sometimes you can think of the lightning activity as the pulse, as though we're measuring the pulse of the storms, and the activity can either increase or decrease. And also we can have changes in polarity. We said most of the lightning is negative to the ground, but often before we see severe weather like tornadoes or hailstorms or severe windstorms, we see an increase in the polarity of positive lightning, the rare type of lightning. So by tracking lightning activity in space and time, we can also say something about what's happening in the storm and maybe even give early warnings for severe weather. And if I show one example from China, again, if we see the thunderstorms positive at the top, negative at the bottom, most of the cloud-to-ground lightning, it brings negative charge to the ground. And if we look at this time series, we see that the total lightning is often fairly close to the cloud-to-ground lightning, the negative cloud-to-ground lightning. The dotted line and the bars match each other. The positive lightning, which is quite rare, is the black line. And we see that when we have the hail falling on the ground during this blue period, you can see a dramatic rise in the positive lightning relative to the negative. And on the top right, if we look at the actual spatial distribution of the lightning and where the hail fell, the gray dots are the normal negative lightning, and the pluses show you where we have clusters of positive lightning. And this is exactly where the hail was measured at the ground, the hailstorm. Hail is a big problem for agriculture, for example. You can see the pictures here and the bottom, also for property. And so lightning can also give us some information about the type of weather we're going to have in the near future. So let's talk a little bit about how we actually monitor lightning. So lightning on the ground is generally measured using radio waves. So we need to have a bunch of antenna, either measuring the electric field or the magnetic field from the radiation which is emitted from lightning. So if we have a lightning flash, it will radiate in all different frequencies. Most of the energy is in the very low frequency, what we call VLF range, which is around about 5 to 10 kilohertz. And this radiation will propagate in all directions and will be detected by our sensors, which will be at different distances from the lightning channel. And therefore, by looking at the different time of arrival at each station, we can use different 4 or 5 stations to geolocate the lightning. And depending on how many sensors we can, and how close the sensors are, we can get down to maybe accuracies of a few hundred meters if we're on a local regional scale. And if we're looking on a global scale, maybe 5 kilometers anywhere on the planet. So here you can see a network that I'm involved with. It's called the WWLLN. Next slide, you'll see the website. It's basically a university network of more than 70 stations. The circles, you can see where the antenna are located. If there's a red star in the middle, means that it's active in this image. So here's Tel Aviv. And we basically are only saving the time that the pulses are coming into our station. And this goes to a processing unit. And if we look at all the pulses within, say, 30 microseconds, we can cross-calibrate and compare the data and the different time of arrival. And then we get these blue dots on the map, which are showing us the location of the lightning activity. You can see the time and the date above. This is on an hourly scale, but we can get the data at any time resolution. In the background, you can see the infrared images from satellites so that we can see this day and night. The red line coming across the plot is the terminator of sunrise and sunset. So the infrared isn't influenced by that, so we can see the storms and how they propagate in the tropics or in any location. And we can look at a plot just from yesterday. So this is the website, www.lln.net. You can go in there and see more or less the real-time lightning activity. This was for yesterday at 13:50 GMT. The little green dots are the stations. You can see day and the nighttime. And now it's basically winter in the winter months, although here in Israel we have had in the last few days thunderstorms and we have winter lightning from the Mediterranean. You can see most of the lightning is in the southern hemisphere where it's summer at this time. Now, we've got also satellite data. That was radio data. We have satellites, especially NASA satellites, which have been monitoring lightning from space. This is a 5-year climatology. So the date at the top, you can see running over here is not for a specific year. This is a 5-year mean. And the color shading represents the amount of lightning in every pixel. And the first thing we noticed when we look at global lightning is that it's basically over the land masses. So 90% of the lightning on the planet is over only 30% of the land, 30% of the planet. Very little lightning over the oceans. We think this is mainly due to thermodynamics, that the daily heating by the sun over the land, we have a very strong diurnal cycle in temperature. The energy of the sun heats just a very thin layer of soil, and therefore the air temperature heats up rapidly in the afternoon and leaves us to convection and instability in the late afternoon in the tropics. Over the oceans, that same energy goes into meters of water, and therefore the actual ocean temperature doesn't change that much over the diurnal cycle for a specific day. It changes between summer and winter, but we don't have the huge instabilities that develop, say, in tropical Africa, over the Amazon, Southeast Asia, in the late afternoons in the tropics. So the first thing is interesting we found is that most of the lightning is over the land where people live, obviously. And so this is important for public safety. In addition, you can see the migration of the lightning north and south of the equator. Lightning is mainly in the summer hemisphere, so now in June, July, August, north of the equator, and then in December, January, February, mainly south of the equator, except for some warm ocean currents like the Mediterranean, the Gulf Stream, a Gulf current, which have lightning over the sea in the winter season. Overall, when we count up how much lightning and how many thunderstorms we have, turns out we have between 1,000 to 2,000 thunderstorms active at any time while we're sitting here somewhere on the planet. And it amounts to about 50 to 100 lightning discharges every second of the day. We have lightning discharging within these thunderstorms. So continuously we have thunderstorms and continuously there's lightning activity. And in the recent years, a new area of research is looking at the Arctic, and it turns out that in the Arctic, we're starting to see a rise in lightning activity. Obviously, this is summer lightning. We don't have any lightning in the winter, but we're seeing more and more lightning in the Arctic, which can have, again, ramifications for wildfires and for other factors. So this is also something worrying. So the first question we can, before I go to the next one, here we can see the most recent data. We also have now satellite data on geostationary data, lightning data on geostationary satellites. The European satellite, the MTG, went up 2 years ago, and we're starting to get the lightning data from there, although it's not publicly available yet. This is from the American geostationary satellite. You can see all the yellow flashes. This is the real-time or the lightning data, which you can see overlaid on the infrared. This is a whole new different period now of studying lightning, because we can see it continuously in time, and it's giving us from one sensor, we can see the whole hemisphere and all the lightning across the hemisphere. So we're learning a lot more things now about thunderstorms and lightning using the geostationary satellite data. So the first question people ask is, have thunderstorms and lightning changed in the past decades? Well, we don't have too much data of actual lightning. The networks have been running for maybe 10, 20 years. We need maybe longer to see trends. And the problem with a lot of the networks is that they keep adding sensors so that we're getting better detection efficiency all the time. So it's difficult to really compare what happened 10, 20 years ago to what's happening today. But one of the meteorological parameters that's been measured for more than 100 years is something called thunder days. And this is measured by the observers in weather stations, in weather offices around the world. Thunder days are days where thunder has been heard outside. So it's not the best parameter, because if there's one clap of thunder, or if there are 100, it's still regarded as just one day. And you can have a maximum of 365 days in the year or 30 days in the month. But we have fairly long time series of this. And here you can see an example from Sao Paulo, which shows that from the 1950s, does appear that there's been an increase in the days with thunderstorms, going from around about 60 days up to closer to 90 days by the year 2000, and possibly linked to the warming, the increase in temperature, which here it's about 3.6 degrees per century, the slope of this curve. And this gives a sensitivity of about a 10% increase in thunder days for every 1 degree warming. And we'll come back to these numbers, since they seem to be fairly robust in different studies. We can also look in other locations. And again, as I mentioned, going into the Arctic, if we look at Alaska, 65 north, although they don't have much lightning or thunderstorms, you can see that from the 1950s, they had maybe 4 days a year with thunderstorms. This has gone up to maybe 10 days a year, so still not a significant amount, but definitely, and there's a lot of scatter as well. But this would imply a 300% change over a century. In Southeast Australia, we can also see from the 1940s onwards an increase. Japan has also got data from the 1930s, 40s. And so many places around the world where we have this thunder day data, we see increases which are occurring over the 20th century. There are some locations which also show decreases, but the majority show increases in thunderstorm activity or thunder day activity over the 20th century. We've also tried to use reanalysis data to estimate thunderstorms, say, over Africa. So this is over Africa, looking from the 1950s or 1948 with the reanalysis data and building an empirical model based on lightning activity today to try to find out climate parameters which are best related to this, and then to go back in time and use only the climate parameters to give us an estimate of thunderstorm activity over Africa. And this is not actually the lightning, it's the number of thunderstorm cells we have. And this also appears to have increased quite dramatically from 1950s to the end. This is going into 2015. And it also appears to be there's a link with temperature, that warmer years appear to have more thunderstorms and cooler years have less thunderstorms over Africa. And if we look at the sensitivity of those, we can look at both the number of these thunderstorms over Africa and also the area, how big they are. And we basically, first of all, there's a correlation coefficient here of 0.74, 0.75, implying that the temperature variations over Africa can explain maybe 55% of the variability in thunderstorms. And if we try to fit this with the line, we see about a 40% increase in the number of thunderstorms for every 1 degree warming between 1950 and 2010. So the next question is, what will happen in the future? And what do we expect to happen due to rising greenhouse gases? So here we need to use climate models. And this was my original work for my PhD, was to try to see how we could calculate lightning activity in GCMs, since we all know that the GCMs are very coarse spatial resolution, whereas thunderstorms occur on much smaller spatial scales, and therefore we need to develop parameterizations. And so this was work which I did a long time ago. But if we look at what may happen with the different scenarios from the IPCC, again, it depends what we're going to do. And so obviously we have to run models for different scenarios to see what's likely to happen in the future. So from my PhD, we developed this very simple relationship looking at a link between the flash frequency in GCMs and the height. H is the height of the convective clouds in every grid box and at every time step. And we have a different relationship over the oceans and over the land. And we also have a relationship to separate out the lightning in the clouds and to the ground based on the thickness of the cold portion of the cloud. In other words, what's the depth from the 0 degree isotherm to the top of the cloud. And although this was published first in 1992, I'm very surprised that in 2023, people are still using this simple relationship. Others have been tested and worked on, and I'll show you some results. But because of its simplicity, maybe people prefer to use it. And the results seem to be fairly good at simulating what we see in the real world for today's climate. And to show a comparison of basically the satellite observations for June, July, August, and December, January, February. Again, the lightning activity mainly in the northern hemisphere and over the land areas in June, July, August, and in the southern hemisphere in December, January, February, compared with the control model for the climate model for the same months, June, July, August, and December, January, February. We see a fairly good agreement between the three main tropical centers of lightning activity, not much over the oceans, and the seasonal distribution as well. And when we double the carbon dioxide in the atmosphere, so this is a model from some time ago, but the NASA GISS model 2, where we double instantaneously the CO2, the equilibrium warming is 3.8 degrees by 2100. And if we look at the change in lightning activity from 2000 to 2100, it's about a 50% increase, giving us, again, a sensitivity of about, for every 1 degree global warming, about a 10% increase in global lightning activity. I wouldn't put too much weight on where the lightning is occurring. This may vary by the convective schemes in different models, but generally where we have the lightning today in the models, they show an increase in the lightning activity. More recently, other people have been looking into this, and we can see different parameterization. So this is from Clark et al. 2017, looking at the percentage change in lightning flash density for every degree warming. So this is looking at the difference between 1996 to 2005 for the control run and 2079 to 2088 for the future climate. PR is the price and Rhine. This is our parameterization, the very first one, which is still being used today. The open and the closed bars represent the different scenarios, the RCP 4.5 and 8.5. The triangles in the circle represent the changes over land compared with ocean. And the different colors represent different parameterizations, which are using mass flux, using precipitation, CAPE, all different parameters in models. And except for one which actually got a lot of publicity because it's different to the others, this mass flux one, which shows actually a small decrease for the highest scenario. All of the others show increases in lightning in the future, including this paper which uses the other parameterizations that also shows an increase. So something about this mass flux parameterization seems to be somewhat strange. But again, you can see that the overall increases for the different parameterizations are around about 10% increase for 1 degree warming. So there's still work to be done here, but generally, I think if you collect all the studies done, the jury basically claims that there'll be about a 10% increase as the climate warms, although it'll be very different in different places. This is the global changes, and it could get up to 50–60% on specific continents and in the tropics. Now, besides the climate impacting the lightning, can the lightning itself feed back on the climate? So the answer is yes, and this first of all through tropospheric chemistry, primarily through the production of NOx, nitrogen oxides, which then are the precursors of ozone, specifically tropospheric ozone. And we know the tropospheric ozone is a greenhouse gas. So when we fly planes through thunderstorms, and you can see the rise here in water vapor showing more or less where the clouds are, we get these big spikes in NOx production. And these are the spikes measured close by to lightning discharges. Lightning channel can get up to 30,000 degrees. And so it breaks up all the molecules in the air. We have dissociation of basically everything, and then new molecules form. So NOx is formed, and then NOx can have a fairly long lifetime in the upper troposphere. In fact, when we look at the vertical distribution of the NOx for different field experiments from Southern Africa, Brazil, Colorado, New Mexico, the vertical axis is altitude. We see that actually in the upper troposphere, in the anvils of these storms, where the updrafts are taking the NOx high, we have very high concentrations of nitrogen oxides. And then once the clouds disperse, this can have lifetimes of days in the upper troposphere, and therefore can spread around, disperse, and produce ozone, which can then act as a greenhouse gas. And if we look at the impact of all the different sources of NOx on ozone in the atmosphere, what we see here is each panel is a different source. We have lightning up here, biomass burning, soils, ships, land transportation, industry, air traffic, stratospheric production, oxygen photolysis, and every panel is showing the latitudinal distribution or the zonal distribution from the South Pole to the North Pole, and pressure or altitude. And what we basically see is that in the tropical atmosphere, and particularly in the southern hemisphere, which is relatively clean, lightning is the main source, the most important source of ozone. So this is showing the sources of ozone because of NOx production. And so lightning is the most important tropical and southern hemisphere source of ozone in the lower atmosphere. So significant when we're talking about greenhouse gases and ozone formation. But another important factor from thunderstorms is the transport of water vapor into the upper atmosphere. So through the Hadley circulation and the Walker circulation, we know that in the tropics we can get deep convection. The anvils of ice will eventually sublimate. And we can see in this animation that the water vapor shown in gray gets advected away from the tropics, but remains in the upper troposphere. And water vapor itself is a fairly strong greenhouse gas. And in a recent paper, which came out just a few months ago, we looked at global lightning on a global map and compared this with the specific humidity in the upper atmosphere. So we have here the specific humidity in a 5-degree lat-long box over a year. So we're talking about 36 by 72 grid boxes times 365 days. This is the lightning, and the colors represent the different months. It's not important the details, but we see that as we have more lightning activity, although there's a lot of spread here, we also see we get more specific humidity, more absolute humidity in the upper troposphere, around 200 hectopascals or millibars. And this water vapor can go also to producing cirrus clouds, which also have a warming effect. And therefore, thunderstorms themselves are generating positive feedbacks in the atmosphere, which can enhance the warming that we already have from the greenhouse gases. And that's more or less what I just showed, just in a different plot. That basically, if we increase the thunderstorms, we increase the upper tropospheric water vapor, this will increase the surface temperature and will increase again the thunderstorms, and we have this feedback process to amplify the surface warming. So I think I'll conclude here and leave time for questions, although there's one more slide after this. Basically, there are about 1,500 thunderstorms active anytime as we're sitting here during this talk, and with approximately 50 to 100 lightning flashes every second of the day. Lightning is a hazard to the public, to aviation, to the energy sector, forestry, and as I've also shown, lightning, monitoring lightning in real time can provide early warnings for these hazards, both we can use this for nowcasting, for the energy sector, also for aviation, but it also supplies information about the risks of severe weather. Are we going to have hailstorms, tornadoes, severe wind? We also did a study, which I haven't shown here, on tropical storms, where we show that the electrical activity inside the hurricanes peaks approximately 1 day before the maximum wind speed, the maximum intensity of the tropical storms. And so you even have, say, a 24-hour lead time before you get to the peak intensity of the storms. And since the tropical storms and hurricanes spend most of their lifetime over the oceans, where it's difficult to monitor them, lightning activity, which we can monitor from thousands of kilometers away and now from satellites, may be a good tool to monitor the development of tropical storms as well. It appears that the number of thunder days with thunderstorm, has increased significantly in many locations around the globe over the 20th century. And when we look into the future, the lightning activity, we need to use GCMs to simulate this, but the majority of the models show increases of about 10% in lightning activity for every 1 degree rise in temperature, in global temperatures. In addition to the increasing temperature impacting lightning, lightning itself can impact the climate and thunderstorms themselves by changing both the tropospheric ozone concentrations, while also impacting the upper tropospheric water vapor concentrations. Both of these are strong greenhouse gases, and the water vapor can also influence additional cirrus clouds, which can also have an additional warming. And finally, the lightning itself, if we have more lightning, we may have more wildfires in a drier climate, especially in the summer months, and this can again feed back with more carbon emissions from the biosphere. However, even without climate change, the population's growing, and especially in the developing world, and where we have most of the lightning in the tropical countries. And we're seeing there's an increasing risk to the public and especially to farmers who are working outside in the summer months. We see that there are statistics of increasing fatalities and casualties from lightning in these countries. And so in addition to climate change, we also have increasing population, dramatic growth in some countries, especially in Central Africa, which are increasing the hazard and the risks to the population. And while these hazards, it's maybe difficult to control these hazards, we can reduce the risk to the public and to infrastructures by using lightning protection, especially on buildings and schools, together with educational programs to teach the public about what to do at the times of thunderstorms. There was a story in Africa a few years ago, I think about 7 years ago, where a school building which has got corrugated metal roof, no protection, was hit by lightning, and 23 kids were killed in one day. And since then, there have been organizations which have developed to try to help add protection to schools, particularly public buildings in Africa, in tropical Africa, to protect from these kind of accidents. And so while hazards will continue, there are ways to protect both the public and infrastructures, power plants, even maybe wind turbines from these hazards. But related to the education, I'll conclude by saying there are two networks which have developed, education networks that I'm linked to. One is called the ACLI-net, which is focused mainly on Africa, which is dedicated to decreasing the deaths, injuries, and property damage in lightning in Africa. This is one of the organizations that's trying to put up simple lightning protection onto schools, onto public facilities in Uganda and other African countries, with a number of pilot projects around also Lake Victoria to try to help protect the public, but protection is not enough. Also education to try to explain the science of what is lightning, that this is not something from the gods and people are being punished if they get killed by lightning. And the other network, the SAL network, is in the South Asia region, mainly India, Nepal, Bangladesh, Sri Lanka. We're here too. I was surprised to hear that 3,000 people are killed just in India every year by lightning. And those are the ones reported, the people who get taken to hospital, and there's probably many more. And again, a lot of ignorance about what lightning is. We need education, both in the school level to the farmers, and early warning systems, maybe even through smartphones or cell phones, to warn people that storms will be there in the next, say, 30 minutes, to allow them to take cover, but they need to take cover, obviously, in buildings which are protected from the lightning. So I think I'll end there, and if there are any questions, I'll be happy to answer.
Yes, thank you very much. That was a very interesting presentation, going through a lot of research. Is there any questions? I don't see anything yet in the chat, but maybe someone in the audience you can raise your hand and unmute and show your I mean, yeah, or you can just put it in the chat. I had, while we're waiting for potential people to ask questions, I have a question. So you showed the results between the different methods, and you showed that, or the conclusion was from this plot, these bar plots or histogram, you said all the methods apart from one are showing an increase in lightning, but it was only over land. In ocean, some methods showed a decrease in ocean lightning. Can you explain that?
Yeah, I'm not sure from the models, but generally, as I showed, there's very little lightning over the ocean. So it's maybe 10% of all of the lightning is over the ocean. So I'm not sure how significant those changes are. So I haven't looked into the detail in those models really. Most of the change, in which will also impact the public and industries, over the land areas.
Yeah.
So I can't really comment on that. Obviously, we do see that if you have more convection and more thunderstorms in one location, then you also have, this has to go down somewhere. So you have maybe subsidence in other places. And so you may have more intense convection over the tropical land masses, but this will actually then result in maybe more subsidence over the oceans, which will maybe reduce the lightning over the ocean areas.
Yeah. Yeah, and I mean, what obviously was apparent in your plots was that the Mediterranean Sea has, yeah, because it's a warm sea, it has a lot of lightning, and
Well,
uh,
only in the winter. So I live here in the Mediterranean, but the lightning is only winter
oh,
lightning over the Mediterranean Sea. So most of the hot spots over the sea are where you have warm water, but cold air you have above in the winter coming, say, from Europe. So we have here most of our lightning is in the winter over the sea, the same as the Sea of Japan, the Agulhas. But in the summer months, there's very little lightning over the Mediterranean. And then you
hmm.
have a lot more over Europe and over the land masses.
I think that connects well to the question that is in the chat. Cheng Ta, you have raised your hand. Is that your, yeah, maybe you ask your question directly. Yeah.
Yes, one question that I have is it seems to me that the lightning and the thunderstorm are certainly associated with the convective activity. And then traditionally in the tropics, when there's a